According to the program, we now start the working part of our workshop. Irrespective of the name of Tampere meeting, seminar in 1983, conference in 1987, or workshop just now, emphasis always was here on interactions between statistics and linear algebra. This is especially emphasized here. The opening talk of the working part of this workshop will be interface between statistics and linear algebra. It's a great honor and pleasure to introduce the speaker, Professor Ingram Olkin. Since 1961, Ingram Olkin holds a joint professor of statistics and professor of education at Stanford University. He is very well known as an outsider. 100 research papers and 5 books. Several of them are now classics, to mention only a joint book with All Marshall on majorization theory. He is also very well known as editor, to mention only that Professor Olkin was the last editor of the Annals of Mathematical Statistics and the first editor of the Annals of Statistics after splitting the annals. Ladies and gentlemen, interface between statistics and linear algebra, Professor Ingram Olkin.
Thank you. Yes. Okay. Can we put that right over here? John Tukey has always used 2 projectors, so I asked for 3 of them, but they only had 2. So, well, oh, you have it over there. Okay, well. Wait, excuse me. Is it possible to put that one over here? I don't think so. No? It's, well, okay.
See, this is why he used only 2. See, with 3 it doesn't work. 2 is country and 3 is a crowd.
I don't think it will, I'll use this very much. I'm sorry to break the spell from the last talk, which was really a lovely talk, and to get down to a different kind of business. I gave a talk on the interface between statistics and linear algebra at a previous conference for the Society of Applied Mathematics. And there, because they were mathematicians, I tried to emphasize a lot of the ideas in statistics and to show how linear algebra came into the picture. So the can I ask you a favor? Could we move this down one notch, please? I think it would be clearer. Much better. Okay. And so there I emphasized linear algebra with the statistical ideas. And when I discussed giving a similar talk here, I really did not want to do the same things that I did there. And so, and since here we have the statisticians, I'll try to emphasize the linear algebra. So I've called this interface 2, and I'll discuss a different set of ideas: game theory, functional equations, generating random matrices, moment-type inequalities, order statistics inequalities, factor analysis models. I won't be able to do all of these, so I'll try to cover as many as I can. The first is game theory. Now, game theory has a lot of potential, and I want to mention just a idea of why someone might think about game theory in terms of statistics and in terms of linear algebra. Well, there's the very famous Courant-Fisher representation that if you have a symmetric matrix A with characteristic roots lambda, and I will almost always use the order lambda 1 down to lambda n if I don't state it again. Well, the Courant-Fisher theorem says that the kth characteristic root can be represented in terms of a minimum and a maximum of a quadratic form with divided by xx prime, or where xx prime is 1. The maximum is taken over all x which are orthogonal to a y, to yk, and the y's are taken with respect to orthogonal, all the others orthogonal with respect to, all the others should be orthogonal to yk. Now, recently there have been a number of other Minimax results. Let me, just for the record, let me state the von Neumann Minimax theorem. This is the well-known Minimax theorem that if you take the sup and the inf of the bilinear form, it's equal to the inf in the sup, and that's equal to the value of the game. And the inf and the sup are taken over all probability vectors where the probabilities can be greater than or equal to 0 and add up to 1. Already in 1950, we have the beginnings again of an inkling of a Minimax result. This is due to Wieland. If you have an irreducible matrix A that is non-negative elements and the nth power has all positive elements, then the spectral radius can be represented as a max and a min. Max of a min and also min of a max. Now, Berghoff...
Overhead is not very well seen from here.
You cannot see it?
Background.
Is that why you can't see it, or is it my writing?
It's too small, but the big theorem is
Too small. Okay.
Oh, yeah, better. Still big.
Okay. All right. Berghoff and Varga in 1958 showed that, again, if you have an irreducible matrix, the spectral radius is the sup and the inf. Now, very recently, there have been results by Dansker and Varadhan in which they again represented the spectral radius as a sup and inf. P plus indicates that the probability vector cannot have any zero probabilities. And now AY1 is you take the matrix A times the vector Y, that's a vector, and it's the first element or the nth element. Okay, so what I've tried to show here is that min-max type of arguments come in with characteristic roots. Now let me show how game theory helped in a probabilistic setting. I was involved with Al Marshall on some Chebyshev inequalities, and there's a classical procedure for generating Chebyshev inequalities, a very easy kind of procedure. Suppose I have a random vector, and I'm given certain moments. The f's are certain functions. F1 we take to be identically 1. And what we know are the moments of F1 up to Fr. Now I want to find a bound for the probability that x is in some closed set T. The solution is very easy. Namely, you take the probability is less than or equal to a vector A times phi prime, which was given, that vector, and you take the inf over all A. And what are the A's? The legitimate A's is that AF prime, this vector, is non-negative, and it's bigger than 1 on T. All Chebyshev inequalities come from that very, very simple idea. What's remarkable is that this idea, this very simple inequality, gives you a sharp bound. So the question is, how can we show sharpness? Now, there are a number of proofs of this, and I want to just give an example where game theory came into the picture. Let me give an example from a multivariate version. Suppose I have an n-dimensional random vector, mean mu, covariance, or second moment matrix sigma. Define u as 1x, then the covariance matrix of u is 1 mu, mu prime sigma. That's some positive definite matrix. Now, to find the probability that x is in some region T, this is less than or equal to the inf of trace A pi, and A will now be over all matrices A, which are positive semi-definite, and UAU prime is greater than 1 for x and T. What I want to do is translate this into a game. So let me translate this into a game. Suppose we have points, m points in k-dimensional space. Define a matrix T, which are the u's. Remember, I have the x's, and for each x I get a u. So for each x I get a u, and these strung along as columns give me the matrix T. Now I have some probabilities which I don't know, and if I have the covariance matrix of those x's, then this T dp T prime will be a covariance matrix. So H is the covariance matrix for the points x's and with the probabilities p's. And I wiggle T to mean that these points are in the set T. So the condition that UAU prime greater than or equal to 1, which was the condition over which we have the inf, is equivalent to the trace of AH greater than or equal to 1 for H in T, or H corresponding to T. So now I have A is this new set, and what I have been able to accomplish here is I don't like this set, because this set involves the U's and the A's. Now I have a nice matrix H. Now I do a little algebra. The inf of trace H pi, remember that was our bound. So that inf I can rewrite as an inf over another set. I can do a little inversion, and then the key is I can write it as a soup of an inf, and now I have it in this format. In this format, I have a game. Namely, one player chooses a matrix S, the other player chooses one player chooses a matrix S in the set S. It has to be positive semi-definite. The trace of S pi is less than or equal to 1. So any S such that, remember, pi was given, such that this holds is a valid S. Player 2 chooses a set of points and a probability vector and gets a covariance matrix. The value of the game is trace of SH. when you show that the game has a value, that there are optimum strategies, then you've shown that there exist points that achieve the bound. And that was the idea in in showing sharpness. So the first part that I wanted to talk about was some ideas on game theory. I think it's a very useful idea when it works. The second is functional equations. Functional equations has a very, very long history. One of the places where functional equations comes in a very, very natural way are characterizations. And the example I've just put down is, I've just chosen one of the earliest examples. There are now hundreds, and I'll talk about one or two more, is the Levy conjecture in the Cramer proof, that if x and y are independent and x plus y is normal, that x and y are normal. That says that there's a certain functional equation in the characteristic functions, which was solved by Cramer. If one assumes densities, then this is this functional equation. And as far as I know, nobody has actually come up with a proof that these densities, assuming some appropriate conditions, that these are the normal distributions. But there are many, many results, and the classic book is by Kagan, Linnick, and Rao, in which they talk about characterizations of many distributions. So that's one big area. But there are lots of other areas, and my purpose here is actually to give you an indication of different kinds of places where functional equations come in. There's a very pretty proof in the Annals of Mathematical Statistics by Roche, who is in Sweden, in Denmark. Excuse me. I apologize to everybody. I know that may be a sore mistake. Roche has a very nice proof as follows. Suppose we assume that the distribution of the x's is of the form xx prime. So we have some function h of x prime. The Wishart distribution is the distribution of v, which is xx prime. And here's how Roche does it. He takes two different roads. One road says, suppose v is xx prime. Then v, the joint density of the v's, will be h, which is exactly this, times some unknown v. No j of v. So he takes a second route. The second route says, let x equal ay. All right, now let's get the distribution of y. So we just put in for x ay. We have ay, y prime, a prime. But we know the Jacobian of this linear transformation. It's the determinant of a to the nth. Then he says, let w equal y prime. So now for y prime, we put in w. This is the same. But now we still have this unknown function, because that's the function you get when you take v equal xx prime or w equal y prime. Now let v equal awa prime. And so p of v is h of v, a to the nth, j and w. And now I have the Jacobian of this transformation, which I know. So now we have two routes. One route gave us this star. One route gave us that star. They're equal. So for equality, we have this functional equation. This has to hold for all positive semi-definite v and all non-singular a. Well, it's very simple to solve. Take v, the identity, take q equal a prime a inverse, and you get that the solution j of q is a constant times the determinant of q to a power, and the power is the critical point. It's n minus p minus 1 over 2, which is the famous power that comes into the Wishart distribution. So that was Roche's proof. Well, at one time I remembered that proof, and it suggested something to me. Suppose I want to find the Jacobian of a transformation v equal AWA prime. Well, here's a little trick. Let W equal BZB prime. So V is AWA prime, ABZB prime, A prime. Now we have the chain rule. The Jacobian from V to Z is equal to the Jacobian from V to W and from W to Z. So I have the functional equation HAB is equal H of A, H of B. And I assert that that functional equation has a solution, the determinant to a power. The power can now be obtained by just choosing a very simple special case. So now I have to prove that this is the solution. It's not hard to prove. It's in a book by Axel, by the way, Functional Equations. The definitive work is a book by Axel on functional equations. He gives a proof, but not this proof. Every matrix A can be written as the product of symmetric matrices, two symmetric matrices. So I need only consider a symmetric matrix. Now I can factor it, diagonal and orthogonal transpose, but because the condition it's cyclic, H of AB is equal H of BA, this is just equal H of a diagonal. And now I do a little trick. I write the diagonal as a product of diagonals where only one diagonal element appears at each place. So this is lambda 1, 1, 1, 1, 1, 1. Lambda 2 in the second place, 1's elsewhere. Now, from the condition, I have H of the diagonal is H of the product, which is the product of the H's. So now consider any one of these. For example, take the nth. H of dn, and now pi is a permutation matrix. Permute, put pi to be the permutation matrix that takes it from the bottom to the top. So now each one of these goes to the top. So H of the diagonal is H of the product, but the product is the determinant. So this is a function of the determinant. So now I have H of uv is H of u, H of v, but this is a function of the determinant. So this is now a scalar, the product of the determinant of the product is the product of determinants. So we have the famous Cauchy equation, g of xy is g of x, g of y, for which the solution is well known. All right. Let me give one more example of functional equations. This comes up with exponentials. This is some recent work with Al Marshall. Suppose I have k independent, identically distributed variables. Each one I'll call is x. Wk is the minimum. Now it's well known that if k times the minimum has a distribution the same as each x, then I have an exponential, and conversely. Now, this has a long history. It goes back to 1928 with Fisher and Tippett. More recently, it's been extended in different directions by Sethuraman, by Desu. And basically, we have the functional equation that f bar, which is the survival distribution of x over k to the kth power, is f bar of x. And what it was done was it was shown that that functional equation has as a solution exponential. Well, let's talk a little bit about other exponential formats. The Cauchy equation is another well-known equation, and what's interesting is the Cauchy equation is stronger than 2 star is stronger than star, but it has the same set of survival functions. In other words, even though one may have a wider set of solutions, those that are survival functions are the same. So now we come to multivariate versions. One multivariate version is just a straight extension of this one. Another version of the Cauchy is just an extension of this with vectors. It turns out that the second one has only solution that joint distributions where the random variables are independent. Now, an interesting, weaker case than this holds for all x and t. An interesting case is one where x and t are similarly ordered. That means the biggest x is with the biggest t, and so on. Now, this was studied by Marshall and Shackhead, and again, the solution of the weaker one is exactly the same as the other one. Namely, you get the multivariate exponential. The next one says x is a vector, but now E is the vector of ones. So T is a scalar. That's again weaker. That has, again, the same set of solutions. Finally, there's a result of Pickens. He studies this functional equation and gives a representation. And what we have is that B is contained in C, is contained in D, and B is contained in C is contained in E, which is the same as 1, as A. Now, this all relates to a result of Pickens. Here, if we have exponential random variables, we'll say that they're exponentially scaled minima if the minimum of xi over ai is exponential. And Pickens gave a very pretty result that k times wk is the same as x if and only if x has a distribution with exponential scaled minima. Okay, I want to move on to generating random matrices. Here, there are lots of problems in which we have to generate a random matrix. For example, suppose we want to generate a random correlation matrix with a given mean, or a random correlation matrix of the form TT prime, or a random correlation matrix with given eigenvalues. How do you do that? Well, I'll just discuss the first one. If you want to generate a random correlation with a given mean, and let C be the given mean. So now I have to generate some random variables, and it's not hard to do. I can generate a random symmetric matrix with zeros on the diagonal and means of 0 off the diagonal. Then C plus X will have ones on the diagonal. It'll have something off the diagonal. And it will almost be a correlation matrix. Won't necessarily be one. The mean is what I want, but it won't necessarily be a correlation matrix unless I have non-negative characteristic roots. So now what I have to do is I have to choose my x's in such a way that they're random, but it guarantees that the characteristic roots are appropriate. Well, there are a variety of solutions. Marcellia and I had one of them. If you take some uniform random variables on aij, minus aij, and aij, and then what you want is the maximum of these aij's to be bounded in a certain way by this characteristic root, then everything works out. All right. The next big generation problem is how do you generate a random orthogonal matrix according to Haar measure? Lots of discussion on this. One standard procedure is generate random variables, form a matrix, and then use the singular value decomposition. Then the G1 and G2 will be independent. There'll be random correlation orthogonal matrices, and it will be just what we want. There are several other schemes. Orthogonal matrices are related to skew-symmetric matrices. And in fact, every orthogonal matrix can be represented in terms of a skew-symmetric matrix and vice versa. You just have to be careful that certain characteristic roots are appropriate here. But the d epsilons work. This is a very famous formula already due to Cayley. It's also true that G is e to the s, and s is a skew-symmetric matrix. This s is not the same as that s. I don't know of anybody who has been able to implement this representation, but I know lots of implementations of this representation, and this goes back to PL in the late 40s. But we all know a geometric way of generating orthogonal matrices, namely in terms of rotations and reflections. So every orthogonal matrix can be written as a product of orthogonal matrices, where each orthogonal matrix involves an angle. Now, each of these will be of this form. There'll be a 2 by 2, all the others the identity, and the 1, 2 says they're in the first and second place, 2n says they're the second and nth place, and so on. And it'll be cosine minus sine, sine, cosine. And the thetas are between minus 90 degrees and minus pi over 2 plus pi over 2. The epsilons at the end are plus or minus 1. So here's how you generate such a random matrix. You take epsilons plus or minus 1 with probability 1/2, and you take the angle according to this joint density. These are like beta variables, and so they're easy to generate, and then you put them together. And this discussion is in a paper with Anderson, T.W. Anderson, and Underhill, myself. Okay.
How many rotations would you need?
Oh, you just need n times n 1 over 2.
Yeah, that's
Because that's the number of independent.
triangle thing. Yeah.
Exactly. But it works very fast because the key point is that the angles come from beta distributions, and beta variables are quickly generated by the computer. There are a number of very fast algorithms, and that's much faster than generating the whole matrix, multiplying z and then getting decomposition, even though you get it in one fell swoop.
Is it faster than household?
It's faster than household.
Yeah.
And anyone interested, there's a recent review article by I.J. Good and someone else, I've forgotten who, and I all the alternative methods. Moment-type inequalities are really interesting because they have moments and matrices have a certain connection that not everyone is aware of. Let me try to connect the two. Suppose I have a symmetric matrix and take any unit vector and look at the quadratic form u prime. Now, write A, represent A as an orthogonal, diagonal orthogonal, the usual spectral decomposition. Now, UG is also a unit vector. Call that V. So now the quadratic form is V d alpha V prime, which I write as the sum of VI squared alpha I. But the VI squared is non-negative and adds up to 1, so I'll call them PI alpha, PI for VI squared. So what we've now seen is that the quadratic form is the moment, is the mean of a random variable alpha which takes on values at the characteristic roots with probabilities pi. This suggests that every time I say something about a moment, I say in probability, I say something about a quadratic form, because UA to the R U prime is also the rth moment. So let me give you an illustration of a connection between numerical analysis and probability. Here's a theorem from numerical analysis. You give me a matrix A. That's a given matrix. Now pick any vector u of unit length and define mu is uau prime and sigma squared as u a minus mu I squared u prime. Okay? So if you give me this vector u, I get mu and sigma squared. The theorem is there's at least one eigenvalue in the interval mu minus sigma and mu plus sigma. This is called an inclusion-exclusion theorem. So you can pick a number of unit vectors, and then you can find intervals where you have to have at least one eigenvalue. So this helps you in a search. I want to restate this theorem in probability theory. It's well known. You may all recognize it by now because of my notation. Take a random variable z with mean mu and variance sigma squared. Then the famous Chebyshev inequality says that the probability z minus mu less than k sigma is greater than 1 minus k 1 over k squared. So now if k is equal to 1, it says that the probability that z minus mu absolute less than sigma is positive. So it has to have some mass in the interval mu minus sigma, mu plus sigma. All you have to do is translate that. To say there's some mass means there has to be one eigenvalue, because the random variable z is translated to the moment to the mean of alpha. So what we've now discovered is that every Chebyshev inequality is a theorem that has moments, is a theorem about numerical analysis. Well, let me give you an example. Selberg proved the following Chebyshev inequality. Take a random variable x, mean mu, variance sigma squared. I take a constant b greater than some a, which will be in here. Then x minus mu minus a less than b is greater than this quantity under this condition. It's greater than this quantity under this condition. If I choose b squared equal to sigma squared plus a squared, then this is 1. So it's non-negative. So it says there's some mass in the interval mu plus a minus b to mu plus a plus b. Selberg, 1940. Kato, 1949, says there's at least one eigenvalue in this interval, which is exactly the same as this. Each one was proved differently, but not too differently. That is, the numerical analysis proof is very similar to proof in Chebyshev inequalities. Now, I want to point out that instead of a quadratic form, if I take u to be uu prime equal the identity, and if I look at the determinant, that's also a moment. And to see that that's a moment, u prime is, again, the same decomposition. It's v d alpha v prime. Now, this is a k by k matrix. And the determinant of a k by k matrix is the same as the kth compound. But the Binet-Cauchy theorem says the kth compound of a product is the product of compounds. So now, but the kth compound of a k by n matrix is a vector. So this is now a new vector. So this determinant is now a moment of a random variable which takes on values which are the k-tuples of the eigenvalues. Well, there's a lot more to be said, but I don't want to belabor it, and there isn't time. I want to discuss reversal inequalities. Well, the very famous Cauchy-Schwarz inequality is very simple. It says uv prime squared less than or equal to uu prime vv prime. If you take A to be a positive definite matrix, take u as xa to the half, v equal xa to the minus a half, then you generate this inequality. Well known. Another way of saying this, by the way, is to say that E of z E of Z inverse is greater than or equal to 1. In probability, very simple to do. Okay. Now, famous reversal is Chebyshev inequality. That is, I want to go the other direction. Well, I can't go to the other direction unless I have some kind of bounds. And we'll bound these between lambda 1 and lambda n. So this is the famous Chebyshev inequality. It has a tremendous history, and people are working on it even today. I'll briefly go through one or two results, but I really want to show the statistics and the linear algebra ideas rather than just linear algebra. There's one extension by Grube and Reinbold in 1959 that says if B and C are positive definite and they are commutative, then you get a similar thing. Well, I think it's not hard to show. Well, it's immediate that if you take B equal a to the half and C equal a to the minus a half, that you get Kantorovich. But it's also true that that Kantorovich implies Reinbold. So they're equivalent, and I don't want to do that. What I really want to do is tell you a probabilistic proof, because I think there's some intuition here, too. Let's look at XAX prime and XA inverse X prime. And using the decomposition, it's the sum of X, assume it's diagonal with no generality, then it's equal to this. Well, this is the sum of PI. This is the expectation of lambda, the expectation of 1 over lambda. It's not hard to show, to give an argument, that the best bound will be by putting some first. Well, once you've argued that, then all it says is that the best bound is given by this. Well, this is a very nice function. It's concave. It's maximum at a half, and at a half you get the bound. Again, there are probably 30 proofs of this, but Willy Feller always enjoyed giving a probabilistic proof to a mathematical theorem. So I'm following in that vein. I think the probability ideas really clarify what some of the matrix analysis. Let me give a second probability proof, because it again indicates the connections. Okay, suppose Z is a random variable that's bounded between little m and capital M, and little m is positive. Now look at Z inverse. It's a nice function, and if you take little m and capital M, it's bounded by the line. And so therefore, and by the way, you can solve A and B explicitly. So now we have a result, E of Z inverse is less than or equal to A E of Z plus B. That's a stronger result than Kantorovich, because now if I pre-multiply by E of Z, then I have E of Z inverse is less than or equal to this. And this, all you have to do is complete the quadratic form, and you get Kantorovich. So here again, we have a probabilistic result of the matrix theory. But once you see the probabilistic result, there are other reversals that one can look at. There's the famous Lyapunov inequality, which goes in one direction just as the Cauchy-Schwarz did. And again, if you assume that it's bounded, then you can get the best constant, and it's a function of the ratio of m over m. And it's just a little messy, but I don't want to do it. However, the Lyapunov inequality is a very important one. It has many interesting special cases. What are some of the extensions? Some of the extensions were by Bloomfield and Watson, by Knott, by Khatri and Rao, and there are several papers by Khatri and Rao. And their motivation, to some degree, came about because the condition XAX prime determinant XA inverse X prime comes up in the efficiency of certain regression problems. But I want to look at the matrix theory result. of this result, and notice you take the biggest and the smallest, the second biggest and the second smallest, and each of the bounds is like Cantor-Routledge. So this was what Bloomfield and Watson and Knott proved. Khatri and Rao proved the trace result. And now this poses some interesting questions. The first is, suppose we call this matrix, this complete matrix Q. Then the two results say that, that the determinant is less than or equal to the product, and the trace is less than or equal to the sum. This raises an interesting conjecture. Is it true, since the sum is the first elementary symmetric function and the product is the last elementary symmetric function, is it true that the trace of J, that is, the trace of the compound, is less than or equal to the jth elementary symmetric function? I don't know the answer to that. That's an open question. The second is a connection between the trace and the product. The question is, can we obtain an additive version from a multiplicative version, and can we obtain, and vice versa? Now, there's a well-known trick how you obtain an additive version from a multiplicative version, and I'll give an example. Suppose I have two positive definite matrices. This is a multiplicative theorem. It says the determinant, this is the product of the k smallest roots. The product of the k smallest roots of this is greater than or equal to the product of the k smallest roots here to the theta and k here. And of course, when k is equal to n, it says this determinant is greater than this determinant to the theta, this determinant to the theta bar. That's a multiplicative. Now let's get an additive version. Let A be I plus epsilon u, B equal I plus v. For small enough epsilon, u and v will be, this will be positive definite. Let the roots be alpha, beta, and gamma. Now, what does the multiplicative version of this? This will be I plus things. So it will be the product of these. It says that's greater than or equal to the product of these to the theta times the product of these to the theta bar. Expand all of this. This is polynomials. This side is a polynomial. We expand everything to first order epsilon. And so we get this to first order. And now if we let epsilon go to 0, we get an additive version. So the question now is, can you get the, if we start with this result, can we insert I plus epsilon u, I plus epsilon v, and get the additive version, and vice versa? There's a trick to do it backwards. But that gives you a more cohesive system. Again, I'm interested in statistics and positive definiteness. Suppose I have a matrix that I'd like to prove positive definite. Well, there's a nice trick that you can use from statistics. Namely, it says that if I have a positive definite matrix, then there exist Gaussian random variables that have that as the covariance. And if I have random variables, then if I get the covariance matrix, it will be positive definite. So now I want to give a proof of a theorem of Schur, and I want to use statistics. Theorem of Schur says if I have two positive definite matrices, I'm not careful on distinguishing between positive definite, positive semi-definite, but it's just easier to say, but everything works here. Theorem of Schur says that if you take element-wise products, that's also positive definite, semi-definite. Well, I want to give a statistics proof. If A is positive semi-definite, that says that there are random variables that have that as a covariance matrix. If B is positive definite, it has new other random variables, and with B as its covariance matrix. Now form Zi is Xi, Yi. What's the covariance matrix of Z's? Well, the expectation of Zij is just Ai Bij. So that says that C is a covariance matrix, so it must be positive definite. So the theorem of Schur is in this way. Now, you can also give a proof that if A and B are positive semi-definite, that the Kronecker product is positive semi-definite. Here's another example. Suppose I want to prove that that matrix is positive semi-definite. Well, it's easier to prove that it's positive semi-definite in a standard way than the way I'm going to give you. But if you can't sleep at night and you think about this, then you might think that if I have independent, identically distributed, uniform random variables, and if I take the order statistics, that the covariances of the order statistics are exactly these values. Therefore, this has to be positive definite. The same with this matrix. This matrix is easier because if I have random variables and take partial sums, then this will be the right thing. So all I wanted to do was show you some ways in which statistics comes into the picture. Well, I'm now going to talk about quickly about a result that Friedrich Puckelsheim and I were involved in, which is now being regenerated because people are interested in other examples. Friedrich and I gave the solution in one instance. Suppose I give you x and y, and I tell you that the variance of x is sigma, covariance matrix is sigma 1, 1, covariance of y is sigma 2, 2. I want to find the covariance to minimize the distance. And here, the distance we'll take as the expectation of the trace. And so if you want to minimize minus twice the trace of psi is the same as maximizing the trace of psi. Now, we did this in the case of normality, that's here, and in the case of normality, you can write down the explicit solution, and if things are singular, a way of using generalized inverses. But you see, what it says is that how close can two vectors be in terms of the covariance matrix? And if you don't have normality, this is going to involve the Fréchet upper and lower bounds to the joint distributions. Now, those are very hard problems. So Friedrich and I were very lucky. We solved the one problem that everybody agrees is solvable, and we're leaving it up to everybody else to solve the unsolvable ones. Time is short, so I'm going to skip one part. Let me just talk for a second about a factor analytic model. There's a certain factor analytic model. Let me skip this, it gives the background. Essentially, the idea is this. Forget the background. Suppose I know that sigma has this factorization. Now, if I give you an estimate sigma hat of sigma, how do you find estimates of A, C, A1, A2, C1, C2? That's the problem. So, let's minimize the trace. And now, I want to solve, I have these estimates and I want to find estimates here. Well, there have been three proposed solutions. One by Tucker, 58, one by C.R. Rao, 65, one by Christov in 67. Each used a slightly different way to solve them. Now, Tucker solved A1, A2 prime, and he solved it for A1 and A2. The problem was his solution was such that it was not necessarily true that the difference was positive definite, which it has to be. So the Tucker solution, people used it when it worked, but not always. Rao's solution does not fall into that problem. Rao used the canonical correlation factorization, and he found, and he gave a solution. Christoph used a different case. Now, the question is, are these solutions related? Are they all different? What is the relationship? Now, please note that if you give me a solution, A1 and an A2 satisfying this, then any A1M, A2M prime inverse is also a solution. So every time you give me one solution, you've given me an infinite number of solutions. So the next question is, are all solutions generated this way? Namely, if I give you two solutions, does this imply that they're connected in this way? The next question is, if I give you any solution, does there exist an M such that you always get the difference positive semi-definite? The answer to each of these is yes. Consequently, all solutions are related in this way. That means that we could have taken the Tucker solution and we could have inserted a matrix H and H inverse such that we did not have this problem. So all solutions are of this form. This is in a paper to appear in linear algebra. Well, there's lots more to be said. I've left out E. One could speak about D for an entire hour, but my purpose really here was to show how certain probabilistic ideas interface with probabilistic statistical ideas interface with linear algebra, and how linear algebra ideas interface with statistics. I hope some of the people find other examples that work. Thank you.